Welcome to session 2 on applied thermal engineering. As we have discussed in the previous session, after studying this course, you are going to get the knowledge on steam and nuclear power plants. At the same time, you are also going to get the knowledge on boilers, their parts, mountings, accessories, compressors and heat exchangers, steam turbines, refrigerators and air conditioners. This session we are going to discuss temperature enthalpy diagram, that is TH diagram, for steam formation at different pressures. We are also going to discuss what are the advantages of superheated steam, steam tables and their uses, and some simple numerical problems on the steam formation. So let us start with temperature versus total heat graph during steam formation. We have studied this session. We have studied this steam formation in the previous session. Here we are going to study the same thing at different pressures. So if you look at the graph, the x-axis is, that is this axis, it is heat addition, and y-axis is temperature. So let us start from point A. Point A to B. It is water is heated up to its saturation temperature. That is for a pressure of P. If the pressure is increased, say to P1, that is this pressure. If the pressure is increased to this pressure, that is P1, then you can see the boiling point also increases. Then if you keep on increasing the pressure of steam formation, you can see that in the graph, the boiling point increases and hence the sensible heat increases. What is sensible heat? It is the heat required to take water from 0 degree centigrade up to its boiling point. So if the boiling point increases, the sensible heat increases. At the same time, the latent heat decreases. You can see that here. Here latent heat is more for less pressure. For higher pressures, latent heat of vaporization is less. So if you keep on increasing the pressure, we will reach a point that is known as critical point, denoted by capital E here. This critical point is the point where the water starts getting converted to steam once it reaches its boiling point. That is, at critical point, the latent heat of vaporization is equal to 0. That means water starts boiling at this 374.15 degrees centigrade. Once the water reaches this critical temperature, then immediately the water is converted into steam. Therefore, latent heat of vaporization is 0. And this point E is called critical point. There are critical temperatures and critical pressures. Critical temperature, you can see it is 374.15 degrees centigrade. It is the temperature corresponding to critical point. That means the boiling point of water is 374.15 degrees centigrade at critical pressure. Similarly, the pressure, that is critical pressure, corresponding to critical point E is 221.2 bars. That means the pressure at this point, point E, is the critical pressure. So from this graph, we can study that as you increase the pressure, the sensible heat increases and latent heat of vaporization decreases. Then at critical point, the water starts getting converted into steam the moment it reaches its boiling point. That is, once you reach the boiling point, the water is converted to steam directly. That is at this particular critical point. So that is seen by this graph. But generally, during steam formation, the pressure is kept constant. The pressure, it can be pressure of P or pressure of P1 or pressure of P2 or pressure of PE, like that. In high pressure boilers, the pressure is high. There, latent heat of vaporization is less. So this graph, you can see three different zones. The zone from A to E, the zone from point A to point E is a liquid line. It is also called as water region. It is to the left of this line, A, B, B1, B2, E. So the region A, B, B1, B2 and E to its left is water region. And the region to its right side, that is up to this point, C2, C1, C and A1, up to this point, it is wet steam zone. Here you have got water plus steam particles in suspension. That is the zone between B2, C here, and if pressure is P1, B1 to C1, B2 to C2. So it is this area. You can see this area. From here to here, this zone is water plus steam zone. You can have wet steam in this zone. And to the right, you can see that is the zone from E, C2, C1, C and A1. To its right, you have got superheated steam region. So to the right of this curve, you can see the superheated steam region. And what does this line stand for? It is the dry saturated vapor line. At this dry saturated vapor line, at all these points, you have the dry steam. And here, at this point of curve, at all these left extreme points, you have got water at its boiling point. So, boiling point of water, and here the extreme point is saturation vapor point, that is dry steam points. These are all dry steam points. To its right, you have got superheated steam. So this is the temperature versus total heat graph during steam formation at different pressures. Now we will have to understand why we should heat the steam beyond its saturation point. That is why we need the superheated steam. We have already seen before that when dry steam is further heated, the steam is superheated steam. The process of superheating follows the Charles law because the pressure is kept constant. Charles law states that when pressure is kept constant, temperature increases, volume also increases. If you increase the temperature, volume will increase. That is the Charles law. So what are the advantages of superheated steam? Superheated steam has got more heat content and it has more power to do the work. It does more work when it is passed through the turbine blades. If you pass the wet steam through the turbine blades, or only dry steam through the turbine blades, then less amount of work will be done. So superheating will give you more turbine work or more turbine output. So because of that, you are going to have increased thermal efficiency. So superheating is very necessary. Now, after knowing how the steam is formed, we are supposed to know the steam tables. What are these steam tables? These are nothing but the tabular column of properties of steam. All the properties of the steam are tabulated in the form of steam tables. You can see here, T means it is nothing but the saturation temperature of steam. That is nothing but the boiling point. And in the next column, you can see the pressure of steam formation, that is in bars. Unit of steam pressure is bar. Then various properties, specific volume, internal energy, specific enthalpy, specific entropy. All these things are shown here. These are all the experimental values tabulated in the form of steam tables. So all these properties will change when the pressure of steam formation is changing. You can see when the pressure is 1.03 or 1.013 bar, boiling point is 100 degrees centigrade. And its sensible heat is 419 kilojoules per kg. Then you have HFG, latent heat is 2676 for 1 bar. Once we increase the pressure, as we gradually increase the pressure, what happens here? When the pressure of steam formation is increasing, the boiling point is also increasing. That you can see in the steam table. We have also seen that in the previous graph. So if you increase the pressure, the saturation temperature also increases. Then you can note that once the pressure increases, this sensible heat, which is nothing but HF, that is increasing all the time. HF is increasing all the time, and HFG value is decreasing all the time. Here in my drawing, in my steam table, HFG is not shown. Instead of that, HG is shown. That is enthalpy of the dry steam is shown. That is also increasing. So if you increase the pressure, sensible heat increases and latent heat of vaporization decreases. That is an important point. You can check it in your steam tables also. You are supposed to purchase the steam tables because you are going to solve many problems using the steam tables. Now, we will try to solve some problems based on the knowledge what we have gained so far. The problem is like this: make use of the given data and find the quantity of heat required to produce 1 kg of steam at a pressure of 6 bar at a temperature of 25 degrees centigrade under the following conditions. The conditions are when the steam is wet, having a dryness fraction of 0.9. The second condition, when the steam is dry saturated. The third condition is when it is superheated at a constant pressure at 250 degrees centigrade, assuming the mean or average specific heat of the superheated steam as 2.3 kilojoules per kg degree Kelvin. So there is a problem that is given to you. It's what it says is you are finding the steam is in three different conditions. One, there is wet steam, there is a dry steam, there is superheated steam. In all those three cases, you are finding what is the quantity of heat required. That's all. You are finding what is the quantity of heat required to produce the given quality of steam. So we will solve it here. This is the graph which we are referring again and again, even for solving the problems. So let us start. What is the quantity of heat required to produce wet steam? Let us write the data. The data is pressure of steam formation is 6 bar. P is equal to 6 bar. And what is the water temperature? TW I have written 25 degrees centigrade. Water is already at 25 degrees centigrade. That you can see in the problem. It is given in the problem. You have water at 25 degrees centigrade. For pressure is equal to 6 bar, you have to make use of the steam tables and find what is HF, 670.4 kilojoules per kg, and HFG, that is latent heat of vaporization, that is 2085. These things are obtained from steam tables corresponding to pressure of 6 bar. Without steam tables, there is no way you can solve this problem. So I can show how HF is 670.4 in the steam tables. So pressure is 6 bar. Here it's not 6.178 it is showing. So for 6 bar, assume it is 6 bar. For 6 bar, you can see that it is 6.75. In other steam tables, you will find these values as 6, 7 like that. So this pressure reading you have to note down. 6.178 it is there. For 6 bar, you find out what is HF value. HF value is here. Then HFG will be just after that. So this is how you have to refer the steam tables. So write down the values of HF and HFG from steam tables. Then what is the equation to produce wet steam? H is equal to, H is enthalpy or heat required to produce the steam. Here, HF plus X into HFG, that is the equation. HF from the steam table and X, it is nothing but the dryness fraction. It indicates the quality of the steam, and here it is given that it is 0.9. Dryness fraction is 0.9. So it is the quality of steam. It is 90% dry. So put X equal to 0.9 into HFG, that is 2085. So after substituting, you will get this answer. You need 2546.9 kilojoules of heat is required to produce 1 kg of steam. But in this problem, water is already at 25 degrees centigrade. Some heat is present in water at 25 degrees centigrade. So what is that heat? MCW into delta T. M, that is 1 kg of water. CW is the specific heat of water, that is 4.2 kilojoules per kg Kelvin. Then this delta T is 25. Water is at room temperature, 25 degrees centigrade, minus 0. Why I am taking minus 0? My explanation of sensible heat, all this steam formation started from 0 degrees centigrade, that is point A. So 25 degree means you are somewhere between point A and point B. 25 means you are somewhere between point A and point B. Point B is boiling point. Boiling point is certainly more than 100 degrees centigrade. So 25 is the room temperature. 25 minus 0, that is here. Since water is already having some energy, that energy is calculated as mcw into delta T, that is 105 kilojoules. Hence, heat actually required for us to convert into wet steam, that is 2085 here. This value is obtained from the calculation. Not that. Heat actually required is 2085 minus this 105. So that will be heat actually required is 2085 minus 105. You have to subtract this 105 because heat is already there in water. So after this, you will get 2441.9 kilojoules. That is what you are supposed to find out. Then for dry steam, what is the equation? H is equal to HF plus HFG. That is, HF is 670.4 from steam table. HFG value is 2085. You add that, it is 2755.4. Hence, heat actually required is 2755 minus 105, which we have calculated earlier. That is 2650 kilojoules. That is for dry steam. We are calculating this for dry steam. Dry steam means point C. What is the heat required to produce dry steam? Next, we are finding for superheated steam, enthalpy of superheated steam, H superheated is Hg plus mCp into T superheated minus Ts. Hg is enthalpy of the dry steam. H superheated is equal to Hf plus Hfg, that is this Hg, plus mCp into T super minus Ts. Substitute the values of Hf and Hfg from steam tables. Then m is equal to 1, hence it is not written. Cp is the specific heat of superheated steam, that is 2.3. Then T super, water is there at heated to 250 degrees centigrade. That is here. You have heated the water up to this temperature. And what is this Ts? Ts is saturation temperature, 158.8 it is coming. How it is coming? You have to refer to this steam table. What is the pressure? For 6 bar, if you actually go through your steam table, for 6 bar, it is 158.8. That is this pressure, 6.178. If pressure is 6.178, it is 160. 6 bar, some other types of steam tables will give you that pressure of 6 bar. So pressure to its left, you have got saturation temperature. Here you have to get this temperature, 158.8. You will get. So it is that. So you are getting 2965.16 kilojoules. Then you have to subtract 105 from this value, which we have not done. 2965 minus 105. You will get one answer. So that is the heat required to form the superheated steam. So I will repeat this problem again. You are basically calculating the heat required to produce wet steam, dry steam, and superheated steam. Here, by using this equation, H equal to Hf plus X into Hfg, we have calculated this. Heat present in water at 25 degrees centigrade is this. That is 105 kilojoules. That is okay. Then enthalpy of wet steam is calculated by this equation, 2546. So here actually you have to subtract. Heat actually required is 2546 0.9 minus this 105. This correction you have to make here. 2546.9 minus 105. So you will get the answer, that is heat actually required. Then similarly for dry steam, use this equation H equal to HF plus HFG. You will get this answer. Then you have to subtract this 105 because there is some heat actually present before feeding it to the boiler. That heat is 105. So subtract that 105, you will get this answer. Similarly, for superheated steam, use this equation. Then find, after getting this answer, you have to subtract 105 from this. So if you do that, you will be getting 2,950.16 kilojoules per kg of the steam. So this is how the problem is solved. To solve the problems, you require the help of steam tables.